With Unit 6, Lesson 8, Analyzing Bivariate Data. We're going to look at how just the data in scatter plots, how they work together and how it associates with linear associations, and just in general, more information about how to read our data. So a researcher found an association between a dog's stride and the length of its speed. A stride is just simply how far that dog can step in length. The longer the dog steps, the faster it goes, which makes sense. If it's going to take bigger steps, it's probably going to go faster. So the predicted speed in meters per second, S, is a function of the step length in meters. L is written as this. S is equal to 4 times L minus 1 6/10. It says, what does the rate of change of the function tell you about the association between stride length and speed? So when we talk about this, we know that stride length and speed is dependent on the stride length. So the longer the stride, the faster the animal. When we look in here, we look at this as looking just like slope-intercept form with y equals mx plus b. So we could think about this as y equals 4 times x minus 1 6/10. And what that would tell us is this 4 right here is our rate of change. This is our association that we're looking for, where we look at a rate of change of 4 over 1. Now, what does that mean? When we look at the values that we're given here, we're talking about speed is meters per second, and then the step length is in meters. So when we talk about this value of 4, we're talking about that we're talking about 4 meters for every 1 second of stride. So as we lengthen that stride out there, we're talking about breaking out a stride. Think about a dog at a run, a large dog at a run, and we know that dog is traveling 4 meters every single second as that stride gets out longer and longer and longer. So the association that's here, what does the rate of change tell you, is that we can expect that as we see data on a coordinate plane, we can expect that it would work at some kind of a value where if we're talking about this dog hasn't started running anywhere, we're talking about how it starts out with a rate of something like rise 4, run 1, rise 4, run 1, rise 4, run 1. It would look something like this. Pretty quick data to be able to recognize for that animal. All right, second one right here. I'm going to make this kind of quick. I'm not going to graph the entire thing, but we're talking about animal brains and saying, is there an association between the weight of an animal, or so the weight of an animal's body, and the weight of the animal's brain? We're going to use the data in the table to make a scatter plot and ask, are there any outliers? There is this version right here that you can go to for the digital version. That's what I'm going to go to. And here's what we have. We have a whole bunch of animals: cow, gray wolf, goat, donkey, horse, potter monkey, cat, giraffe, gorilla, human, rhesus monkey, kangaroo, sheep, jaguar, chimpanzee, and pig. And you'll notice there are all kinds of informations, and I think that it's really, really quite fascinating to see the correlation between these and looking at body weight to brain weight, body weight to brain weight. These are body weight in kilograms, brain weight in grams. And then for me, it's even more fascinating to look at the data. Here are these data that are graphed on this coordinate plane. And what we have are some questions that we need to ask. It says, without including any outliers, let me put this right here. Here's the 3 questions that you have in your packet. Without including any outliers, does there appear to be an association between body weight and brain weight? So again, no outliers. When we look at this obviously right here, when we're talking about the human value, there's one right there. That's definitely an outlier. So we're not going to include that one, but look at the rest of these. Does it work? What we can do with this is we could say, yeah, there appears to be some kind of an increase right here. Look at our y-axis as 1,000 and our x-axis is in 50s. So this is definitely increasing much faster than it appears. Each of these lines are by 200 on the vertical. And so we see that there's actually a definite increase here. The association that we could say with this one, when we write this in here, is that after removing the outliers, does there appear to be an association between body weight and brain weight? Yes. As body weight increases, brain weight tends to increase. So we see there's a positive association here. And remember, if I'm going too fast for your writing, please pause the video. You can write your stuff down then. It says, using a piece of pasta and a straight edge, fit a line to your scatter plot and estimate its slope. What does the slope mean in the context of brain and body weight? When we do this, they use a piece of pasta on paper because it's just a small single line. They're talking like spaghetti pasta. And you might try it. I just use a ruler when I'm doing this. And the digital version right here, this is kind of nice because I can grab these little green dots and I can pull this through the data and I can work on pulling up some kind of an association that is going to look like it actually has a good center with it and a good balance with it. Now, when I look here, I'm looking at a couple of dots, specifically these ones right here. How these are fairly close on either side. This is right by the line, right by the line, right by the line. Not too far off, another piece right here. So I'm looking at 5 pieces of data below the line and 5 pieces above the line. I feel like I have that pretty well balanced. And now the question that comes down to this, it says, what does this slope mean in the context of the brain and body weight? Well, when we're talking about these pieces, we're going to estimate the slope first off. And then I see that, let's see if I can find a nice point. Remember, these are quite far off in the values that we're after. Down here on the x-axis, we're going by tens. And going on the vertical, we're going by 200. So I see that we're looking right here. This is about 75 and 200. For one order pair. And then I think I can go ahead and go off of this one. This is going to be 160 and 400. And that gives me an opportunity to be able to figure out approximately where my slope is. Forgive me, I'm trying to draw these order pairs with a mouse. So 75, 200, and 160, 400. When we find our slope right here, we're talking about 400 minus 200 divided by 160 minus 75. So we have 200 divided by, I'm not feeling like thinking a whole lot today, but I think it's going to be somewhere around 85. And then we'll just simplify. 200 divided by 85 gives me 2 and 3/500ths. That means that we're looking at, let's just go like this, 40. I know that they have a common factor of 5. So then I get this kind of slope that's 40/17. What I can establish with this is I'm talking about brain weight is up on top and the body weight is up on the bottom, or is down on the bottom. We know that this is the output and the input. And so what I could estimate with that is I could say for every 17 ounces of body weight, there's 17 kilograms of body weight, there's approximately 40 grams of brain weight. So I could also write this backwards and say approximately 40 grams of brain weight for every 17 kilograms of body weight. Now, this is not perfect. It's not exact because I don't have the exact line of fit. But here's the cool thing is since this says estimate, I get to estimate. I put that line on here and my estimate gives me that line that I feel like is pretty good through the data. But what I need to use that for is I need to make that association and decide, does it really fit the data? Now, the cool thing about this is there's another question that's asked, does the fitted line help you identify more outliers? Well, a couple more outliers, we could potentially, because of where everything is at, we could potentially make a claim for this value right here and this value right here being outliers. These two outliers, we could definitely make that claim and have a legitimate claim based on this. because of where they're given and what they could establish. This one right here is the chimpanzee. I'm not going to try and write all of it out, but that's the chimpanzee. And then when you look out here at the other further one that's just under 200, this is a donkey. Actually, just kidding, this is a pig right here. And so it's really interesting to look at those two pieces and say, you know, based on our fitted line, we could say that a chimpanzee actually has a larger brain than expected with the rest of the data, and a pig has a much smaller brain than associated with the data. And so we could make those claims about the outliers simply because they're far enough off of the other line that they might be actual outliers. We know the human one is certainly an outlier, but that's the associations that we can make based on the fact that we have data that helps us with our claim about how close these data are to the actual trend line that we drew. Okay. The next thing that we're after with this is the equal body dimensions. It says earlier class gathered data on our height and arm span. Well, given our situation, we did not. So sometimes a person's arm span is the same as their height. Is this true for anyone in the class? What I did for this is I actually found another graph of data that I've used in the past. And here's that data for arm span and height. This is working off people that are 150 centimeters high. Arm span, this is for your age students, for middle school age students. And this is real data that's approximately there in centimeters though. So the question is this true for anyone in the class? Well, we could say that it's true for this person right here, and this person right here, and this person, these few of them right here on the line. We could also say it's very close to true for these people that are really close to the line, but then we also see that there's some other data that's really scattered along here where you have somebody that's fairly tall, but their arms are not quite as long as their height. And you have other factors here where you see somebody that's not as tall, but their arms are much longer than their height. And so you think about this with students that are in middle school. It could definitely be there, but you're also growing at different kinds of rates. And so we have to ask that question. Is there anybody in the situation sometimes that, or is there anybody that this information is true for? We can absolutely say yes. So let me see if we can do this. I'm going to bring this over here. We say yes, there is. And we see that those people, their data are on the line of fit. Okay. That line of fit that I actually drew right here has an equation of y equals x. And so that equation that's given right there is, the question is saying, is this a good line of fit for the data? In this, absolutely. That certainly is a yes for these data, because it represents the average of the given data points. Now, why does that matter? When we look at these pieces, when we're talking about this, and we're seeing that representing the average of the data, you notice that there's a very tight line that's followed along with this, there's a lot of data that's associated straight with that line of fit, that there's a lot of data that's very close to it. I don't know how much I can draw on here. So I'm going to try it, we'll see. But when we look at it and we talk about these data, when I go to analyze these data that are really close, I can see that there's a very tight association with all the data here inside the blue line. The rest of these are out just a little bit. So when we examine this scatter plot, which person in your class has the largest ratio between their arm span and their height? Explain or show your reasoning. When we talk about this next question right here, question number 4, what we're talking about is the largest ratio would be the point that's the farthest off the line. I think that you can make an argument for any one of these points that are furthest off the line to say that they have the largest ratio, because their differences will be quite extreme compared to the others. We recognize somebody that has a value right here of approximately 162 for their height, but their arm span is maybe only 152. And you see there's a little difference there. You talk about this person right here, it's maybe 156 on their height and 170 on their arm span. And you can see that there's quite a difference in the ratio of those values comparative to the ones where you get to where you have approximately like 160 and 159. This ratio right here is fairly close to that line that's given with y equals x. So what we're really after with this, like I said in the beginning, is this is going to be just a comparison of the data that we see on scatter plots. We're able to come up with lines of fit to be able to talk about why the data works or why it doesn't work, or to be able to analyze it, to be able to talk about that as a body weight increases, typically the weight of the brain increases. We can look at the dog's stride and see that there's an increase there. We can talk about arm span and person's height and see an association that's there as well. So we collect a lot of data. Looking at our summary, we often collect data in two variables to investigate possible associations between two numerical values, and then use the connections to find and predict more values in the variables. That's the purpose of collecting data. To do that, we follow the steps: collect the data, organize and represent it, and look for an association, identify outliers, try to explain why these points are exceptions to the trend, and describe the association. Use a function that fits the data well. After we've done those pieces, there's still a little bit of thought to it. Although computational systems can help us with analyzing data or with data analysis and graphing the data, finding a function that might fit the data and using that function to make predictions is really important to understand this process and to think about what's actually happening. When we find a function that does not make sense or use a line when the situation suggests that a different model would be more appropriate, we have to understand that that changes the way that the data is interpreted. So keep that in mind. Hopefully this is making some sense off of our data when we look at our different scatter plots, when we look at our arm span and our height, when we look at our animals, and just in general, when we look at any scatter plot, consider that piece about how the data relate to each other, but also how they can relate to a line of fit. That's it for today. Let me know what I can do to help you. Have a great day.